Hello everyone and welcome into yet another live stream. And did I mention how dumb I am, by the way? Yeah, this is obviously another hyper-operational maths thing, Google Docs. But there's a problem. You see, I forgot that I'm an absolute idiot. I'm sorry for the words, but it's true. I didn't mistake and I didn't notice that at the time. Which kind of clears up one thing very much. And it's fine. It's fine. Fixed points don't exist. Fixed points don't exist. Give me a second, I have to solve docs.google.com. Is it that? Is it docs.google.com? Yes, alright. I can go through captcha. But yeah, I obviously messed it up. Because it's idiotic. I forgot about the obviously new order of operations, which basically means that fixed points don't exist. I can just throw them away. They're pointless. It's a bummer. It's a real bummer. Because first of all, this, I mean, I still think it's pretty interesting. It's an interesting question to ask. What anti-operation of a number on itself is equal to, right? But we could graph it actually. Wait, that's a good idea. Desmos.com. I have to use this because, you know, it's Google is not letting me go through. Alright, cool. It's a square t, but it's not square root, it's root. Like this, how do you, well, never mind, just this. Yeah, as you can see, it's not exactly the same as, it's not quite as constant, I would say. The weird thing, the thing that is weird in my opinion in this case, is the fact that it changes so much. Like we have constant offset, and then very complex evolution. I mean, look at that. Unbelievably complex evolution. Is it its highest point? I think it is. No, wait, it's not. No, wait. Yes, it is. With its highest point at 2.7. So, yeah, it gets really complex really quickly. That is still a mystery to me. Yeah. But, first of all, fixed points don't exist. I'm an idiot. Let's just... anti-exponentials. Yeah. Two different ways. When it comes to anti-exponentials, I use this, or we seem to have a problem. It's because, and no more lists, just this equation. And that kind of violates the principle because it's, yeah, that's a problem. Operation is problematic at best because we have number information loss. Yeah, here we just battle information loss. Yes, what's this now? Information was create anti-exponents when calculating. There we go. Great, sick. So that's fixed. Now there's also one thing that I would like to do. So now that we know that fixed points don't exist because I'm an idiot. I'm sorry, it's just been on my mind. I was waiting for. Okay. Yeah, truly equal. That is true. Equality, right? Yeah, it's truly equal, it's not identical. That's the thing I've got to mention. But not identical. And over here, I'll just do not identical. This is identical. This is not identical. This is identical. Cool. Not gonna lie, I did realize that identicality, that's probably it's probably, I just probably stole it from JavaScript, if I'm not mistaken. I think there is something like identicality in JavaScript, right? There is equal that would be equal equal, and identical that would be equal equal equal. I think, I don't know. Anyway, there's one more thing that I really would like to mention, which I find rather sick. I think is very interesting because it is just different from normal maths. It's not okay, it's not revelation, but it's different from normal maths, and I find it exciting. Numbers. So far, wait, is it in the axiom, by the way? It should be in the axiom. Numbers axiom. Of all hyperoperations are integers in relation to a given hyperoperation. That is so very important. I love that I already added it over here. Which means that, yeah. Okay, so basically, so far we've talked a lot about hyperoperations, but not. Should I play some music maybe? Give me a second. It feels very dull here. Just play something good. Gaming, yes. Absolutely, the father. That's what we are doing science to, right? Because we are true. I don't know what to even call myself at this point. All right, cool. So hyperoperations, but not a lot about hyperoperies. I'm a simple man, right? There ain't much you need to make me laugh. So let's examine more closely the first and second numbers axiom. Starting with the first, which is over here. The only numbers that is over are integers. Yes. We make it. That's a reference to me, because I make it. First, and let's do it as second, third, yep. The only numbers that truly exist of all hyperoperations are integers. This would be actually something that would be more convenient to show after we show the second one, so we'll do this one out of order. We'll do this out for... we'll do it out of order because it's... if number exists only in relation to a given... a given... does not say give. A given hyperoperation. That's rather foolish. I should put a disclaimer that this is not a scientific paper, because it's just not. But no, it's just something that I do. So I'm bored. we'll start the second one because it's easier to explain what's happening here. Can I not start the... I don't think I can start the second. I genuinely think I have to start the... Okay, cool. It's a bit of a wall there. Fine, I've switched up. Alright, cool. Self-heading 4, normal text. There we go. Ah, that don't look good. Bold. There we go. I want this to be readable, right? I care about these things. So. Now. What does that mean? Well, the only numbers that truly exist over all hyper operations are integers. Is really easy to understand when you realize that we are starting with integers. Realize, completely misspelled. Starting with integers. Integers and integers can be used by any hyper operation. I don't know if I should provide an example here. I can. Is example 3 up arrow 4 is equal to 12, or no, 10 up arrow 2 is equal to 20, for example. Yeah, I should put this in. But using only addition, yeah, by the way, I'm calling first hyperoperation addition because that's what it is, right? And I could call it, you know, first order hyperoperation, but nobody wants that. The only reason why I'm doing hyperoperations is to generalize stuff, so that, you know, you will have a name for addition, you will have a name for multiplication, you will have a name for exponentiation, but for the rest you can just use numbers because there's quite literally an infinite amount of operations. Quite literally. Alright, but using only addition, it is impossible to create give me a second to correct my thought. Alright, it is impossible to create any other numbers. Alright, set of numbers. What symbol should we use for that? It's hot, tempting, but no. We will use you cannot subtract, add or subtract an integer to integers and end up with something that is not an integer. So what about, I should probably, so about fractions, rational numbers actually, let's be numbers. Do they not exist? Well, they obviously do. but in relation to second hyperoperation. That's the every other number exists only in relation to a given hyperoperation. Once again, it says give. Because in order to get a number that is rational, no, that's wrong. It's not an integer and is rational, you need division. And that's a common theme. That's what will be soon. You'll see what I mean. You need division. That's why we will use a more generalized way to order numbers. I did put numbers into sets to classify numbers. In conventional mathematics, normal mathematics. Yeah, I call it normal because mine is just abnormal. Normal mathematics, we have first integers, then second we have rational numbers, then we have third, which is irrational numbers, and then normal numbers. No, yes, that's what we have in normal. Yeah, there are times I get it, but normal numbers is good enough for now. I guess we could, but that's... Nah, it's fine, that's good enough. The mathematics. I do believe this to be an no, not I do believe. In hyperoperational, by the way, mathematics, let's do like this. Hyperoperational mathematics, not pre-operational, hyper. That's, I can see the confusion. It's not really a word, is it? Hyper-operational mathematics. We instead will classify numbers based on the anti-hyper operation that is needed to create a number. Based on the lowest, I should add that right away. Lowest anti-operation that's needed to create a number. Because, for example, in order to create integers, you can create them with roots. You can create them, yeah, I mean 36, a square root of 36 will give you 6 as an integer. You can create them with division if you want, right? Because, you know, 12 divided by 2 gives you 6. But the lowest hyperoperation, anti-hyperoperation, which you can use to create integers is subtraction, because 12 minus 6 equals 6. On the other hand, when it comes to division, when it comes to rational numbers, the lowest order anti-hyperoperation that can be used to create rational numbers is division. Because subtraction just won't do. You cannot just take two integers and then you know. That got me thinking. Need to create number based on the numbers used in all the lower operations. Yeah. So, so for example, based on propose that A, B, and C are all integers. First of the set, so for that we will need some math notation. What should we use for numbers? For set of numbers, yeah. So I guess something simple. Zeta. Oh fudge! I'm looking for something that's not used very often. Wait. Hey. I don't know. Something. I want something that's not used very often, so that later on won't have any problems. And I don't want to just do another hut, because that's, come on, that's pointless. It feels very tempting to do Omega, because that feels really tempting. I don't know why I'm spending so much time on that. Delta is fine, but Delta means something else actually. It feels very tempting. First, so that's addition. By the way, addition is the first type of operation, right? That's for a reason. It's not zero. It's not zero for a reason. Trust me, I'm a computer scientist. I do like starting indexing stuff with zeros, but it's first for a reason. Because I do believe that if we generalize, first of all, if I could generalize everything, then I do want to do the normal mathematics fun, which means, first of all, look at the properties of the zeroth operation, then look at the properties of the negative operation, so, you know, hyperoperation -7, for example, why not? Then look at properties of rational, irrational, set of numbers, hyperset of numbers 4, hyperset of numbers 5. I think I'm too loud. Okay. Alright, so this set can be created using... Is there a symbol for can be created using? Give me a second. I have to check something. I'll bing it. Is there a mathematical formula full of... mathematical symbol for can be created using chat? Bing, give me. I would use chat GPT if not for the fact that ChatGPT does not allow any VPN users, so whoops. How to properly show in math that the number can be created using if numbers. Just give me some notation for that. I don't want to make up. Making up notation is so scary. People gonna be mad. You know that means something else. Very scary. Just give me 10 is equal to 3 plus 7. Oh, go F yourself, Bing. Awful. I want my GPT. I want my GPT. Oh, my GPT back. Let me check on my phone. I'm gonna check on my phone. Alright, let's go. Chat, openai.com, please. Akcesory ChatGPT! O, jestem... Alright, let's try again. I'm sorry, I was in Italy. I was in Italy. I cannot turn off my VPN on stream. That's scary stuff. I know there's such things. That's very scary. You would... I know you all. You would probably dox me right away. Yeah, you... Surely, that's the only reason. Okay. Is there a mathematical notation for can be created thing? For example, to signify, for example, to represent, for example, rational numbers be not rational integers. I mean, example, this. Using A divided by B and B integers. Oh, that's a fine question to ask. Can be created. Oh, really? That can be created using. Oh, I'm such an idiot. Obviously, rational numbers in notation. Oh, it's equal to. Never mind. It's just using it's equal to. Okay, so it's this is equal to A divided by B. I would like this to be is equal to fraction A Oh, by the way, for one first, I don't remember if I told you that, but you totally can divide by 0 in this case. You cannot compute something as divided by 0, but you can divide by 0 because of because of this you can divide by 0. That's what, it's rather fun because if you divide by 0 and then you multiply by 0, you can cancel them both out. Unless you are computing. In computing, you cannot. This, by the way, is kind of like derivatives, except dumber. way dumber. But they do work very similar to derivatives, actually. Because when you are integrating something, for example, you are basically multiplying something that's practically 0 by practically an infinity. The thing that's practically is there because dividing by 0, multiplying by infinity are very not good things to do, but you know. A is equal to just A, then omega second. You have like a line stop. Rather long story. It is actually quite a long story. Really, you cannot find only as 3 lines. So now, omega 2 then would be in A down arrow B such that A and B, wait, no, in this, such that A and B, and set that 3, that's fine. Yes. Thank you. Such that A and B, there it is, cool, are in omega 1. And over here we can close this. Now, what this is doing, which is really neat, is we can this is already generalized actually. This is already generalized, but we will need one more example to actually show that it's generalized. How? Well, so glad no one asked. There we go. Omega third, right? This is second. And over here, what we would need is we would need down arrow. No, that's outside the equation. Whoops. Down arrow C. And then A, B, B and C. Like this. Now, let's actually use. Give me a second, I have to think about that. Because what that means, that's actually rather great. That's great because that means we have a rational number. I mean, and no, wait, that's. Oh, yeah, all of those should be. Wait, I'm confused now. There's no need for B. I mean, for C. Just B is fine. Yes, like this. And there's a generalized form for this now. We can generalize that, which is great. C A is an integer, and maybe not A, let's use M so that it will be less confusing. Later on we're using A, and there we go. This is already generalized, not even can be generalized. Now we can use this to generalize the omegas. I'm not good at English, I'm doing math here. Omegas for any n. For an n, it would look something like this. And now we've basically divided normal numbers into an infinite amount of subsets. You just pick your favorite and it will work. N minus 1, and over here this will be n. There we go. Infinite amount of subsets, and just pick your poison at this point. You can do, and you can create any number you want, only based on integers, and it is generalized. Now, one more thing that I would like to add is why this works. Why can we divide all the numbers into an infinite amount of infinite numbers? Because that's something that I should mention. In the first omega, we have infinite numbers. We have 1, 2, 3, 4, 5, 6, basically any number you can name, add 1, still is in the omega. Omega has infinite numbers. In omega 2, we have even more than infinite numbers. We have all the rational numbers. Which is, that's a ridiculous amount of numbers because it's, well, more than omega 1. Then in omega 3, we have even more numbers than omega 2. And all of those still fit in just normal numbers. How is that possible? Well, once again, so glad no one asked. So, this. Now, a peculiar thing happened here. Because we just divided normal numbers into an infinite amount of omegas where each omega has exponentially more numbers than the previous one. And where the first omega has an infinite amount of numbers. How is that possible? And that's a good question. How is that possible? I mean, that's crazy. Okay, think about that. Yeah, obviously. Alright, okay, minor correction. How's that possible? Well, it is possible because normal numbers normal numbers have an uncountably infinite amount of numbers inside, which is a lot. That's a lot. And normally we don't really use that in normal conventional math because there is no need. There's just too many numbers. Straight up too many numbers for us to care. So instead we just restricted that. We just restricted that to integers, rational numbers, and then irrational numbers. And that's the cutoff. Because these are not irrational numbers. These are just not. These are all irrational numbers which you can get by rooting a number. Which is still a lot. Don't get me wrong, it's really a lot, but it's not all the numbers. Basically, in order to reach all the numbers, you would need, because every single number basically, every single omega contains in itself the previous omega. It's really easy to see. Basically, if you anti-operate where b is equal to 1, then you just keep the first number. So based on these two, you always have the previous omega inside your new omega. And, well, so each new omega has infinitely more numbers than the previous one. It sounds dumb, but that's what it is. And think about that. For first omega, we have infinity. That's infinite amount of numbers. Second omega, that's an infinite amount of numbers that can be on top, and an infinite amount of numbers that can be on the bottom, right? The normal relation a divided by b. Which means it's infinity times infinity. Which is a lot. It's like infinity squared. Please don't quote me on that. It will be taken out of context. The point is, there are a lot of numbers in normal math. We are not using them because that's not necessary, honestly. We don't need to classify them. But over here, we should. Because what that means is that if we are not using the fourth order hyperoperations, and we are not, no one's using titration, let's be real, then that means we can perform a ridiculous amounts of calculations based on only these. But what's even better is that these omegas contain every single number. They have to. At some point, if you think of any number, right, it has to be obviously infinite, because if you think of a number that does not loop forever, not loop forever, does not go forever without repeating, then it will be just an omega 2. So what's really interesting is that you can think of a number and it will be in one of those omegas. And in that omega, that number can be calculated by using only those operations. Which means based on these, you can calculate pi! With no fancy infinite loops, so you can calculate pi with these! Ain't that insane? Obviously, the omega in which you would be able to calculate pi is... it's a big number, it's a really big number probably. Possibly infinity, but still, that's so insane! That is insane, isn't it? That is rather insane. How is that possible? Well, first... Why first... First of all... Alright, first of all... In normal mathematics, we are not really using all of the numbers. We don't need to. We don't need to. We mostly only use rational numbers. And then everything else is just considered irrational. Yeah, no, you don't really hear about normal numbers that much. Normal numbers are basically numbers that you cannot even write an equation for. That's kind of the best description I can give you. So, for example, the most obvious example is 0 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and like that forever. That's the best example there is of a normal number. Because it never repeats, and first of all, it never repeats, and second of all, you cannot really know its exact value. I mean, you obviously can, but you can calculate it. I'm bad explaining normal numbers. I'm not qualified for the job. We don't need. Then everything is just considered irrational, and sometimes calculated. Irrational numbers, sometimes irrational when we are using roots, but for every other number we just use notation like not that notation. Pi or E or what other numbers are there? Golden ratio, which is this, right? Golden ratio, I'm pretty certain. But what's really interesting about these omegas is that they contain every number, and every number inside can be calculated based on integers using a finite amount of hyper operations, which means that if you find the omega that contains pi, for example, then you can write down a finite equation using hyper operations that could calculate the exact value for pi. I know I have this copied. For pi. That is rather ridiculous. What's more, actually, what's even more interesting is that we even know what that equation would look like. That's what's really interesting. Would look like, yeah. So basically it's just this, except repeated over and over. So it would be, well, I guess we should use like x0 down arrow, because we should start from the end, I'm guessing, right? I mean, if you find the end for this, that's already insane. All you need is just an appropriate number. That's really funny, because then this could be created using... well, actually, now I'm thinking about the structure of this, it would be not so easy to pull off. I think we would need genuinely two numbers here. x00, wait, let me think about this. I'm trying to create an equation right now for calculating pi only using only integers, which is funny. It's funny to think about, right? Obviously, this is all hypothetical, I should add. And also, you know that you would need to find the n for pi, which would be rather crazy. It would be rather crazy, not gonna lie. It's rather bonkers, if I do say so myself. So for division, we would need it to be inside omega. No, for roots we would need something from omega second. And in order to get omega second, we need x. Alright, so first of all, subtraction, yes. Then over here we'd have x1 divided by... Wait, am I going the right direction? No, from left to right you should... Yeah, we should do it from left to right. To modify it as we go, yes. Basically x first. It's hard. It's surprisingly hard. Okay, so basically... Paint. Right, give me paint. So basically we have x, right? 1 minus... And we need to basically end up with omega n. Let's try it for 3 for now. Omega 3 to 3 omega 3, for which we would need... This would be omega 2. I have to break it down like that. Omega 2, omega 2, down, omega 2. And for that we need omega 1, down, omega 1. Omega, yeah, down. But it's still very much funny. In order to get any number in omega 1, just need to follow based on integers. You can use the equation is equal to capital O. Let's brew clowns. Capital O1 is equal to, capital O will basically means any number in omega 0 is equal to just A or x0 for omega 2. It's O equal to x0 down arrow down arrow x1. Yeah, because that's any number in omega 2, then infinite power, you better believe. For omega 3, I just love coming up my own math, because then I don't have to think. Then this down arrow then it's this, because it's the number in then for omega 4 it's this, except we first copy the arrow 1 2 3 4 like this. Oh, that's so great. Oh, it's so sick. 4 5 6 7. Basically this would give you any number in omega 4 based on an integer. Omega 4 is already beyond most of the stuff you normally use in math. Omega 3 and all the roots. So all the roots, all of them. So omega 4 is already way beyond. Now omega 4 is already way beyond any normal, any average calculation in normal mathematics. Yeah. Keep in mind that omega 3 already contains all roots. So omega 4 contains everything you can achieve with iteration and anti-iteration. But what about pi? Well, if you find the appropriate n for pi, I should also use this for n so that it would be muffin. There we go. And for pi, you can use this equation to ln bn2. You can to create an equation for pi. for pi using only integers. Isn't that insane, by the way? By the way, over here we also completely forgot about this, about this. So for n, now 0, yeah. 3, then we'll do ... Over here we'd have n minus 1, n minus 2. This would be always 2, this would be n. That is very much fun though. You cannot tell me it's not fun. Over here we would have 3. You cannot tell me this is not fun. Creating an equation which can calculate pi using only integers. I'm sorry for that. You know, brushing this out. I don't know why. How does that sound? I don't know why. How does that sound? That was actually not that terrible. There we go. Yeah, now over here we would have n plus 2, n plus 3, ... because always the middle will be the same, right? ... and then the end would look very similar to well, the end would be just this. ... and over here we would have 2n minus 1, 2n minus 2, 2n minus 3, 2n minus 4. That is very fun. Okay, I know that there is a proof in math that pi cannot be calculated. I will have to look into that proof, because this proves that it can. Oh no, it proves that it's irrational. Yeah, so pi can be calculated. There we go. That's an equation for calculating pi. If you find the correct n and all the correct x's, which is, you know, only marginally impossible. Now that is, I think my text size is screwed up because I changed it. Now that is pretty amazing. Amazing. Here we have an equation for calculating pi, not you, pi. Yes. Calculating pi using only integers. Because this is only integers, so that's great. Obviously, you would need to find the appropriate n and of the all of the x0, x1, x2. Right. For the music going around, because it's great. By the way, Crimpy, listen, so you see this? This is insanely good. I'm so happy with that. It's such a fun equation. This is an equation for calculating pi using only integers. It's funny. It's funny. Exact value of pi with no infinite sums or nothing like that. This is a finite equation for a finite n. The only problem is you have to find the appropriate n and the x0, x1, x2 up to ... x2n minus 1, which is only marginally impossible. Impossible. Come on, we're gonna fix that. Possible thing. Only marginally impossible. But that is an equation. The only point is integers do anything. Yeah, but I mean the problem here is that. Okay, I should probably walk you through the idea. So basically, you know how in math you have rational numbers, irrational numbers, integers, normal numbers. So I assume you do. I will continue on because latency of the stream is less for some reason. It's just an absolute mess. So messing with me windows. So basically, if we have rational numbers and stuff like that, I don't have my graphical tablet. Oh, it'll look like a mess. Normally we only have basically 4 divisions. I can use my paper. I know why I'm doing that. Normally we have only four divisions. Right? We have integers, rational numbers, irrational numbers, and normal numbers. Yeah, there are some more, but these are the 4 basic ones. Well, because we are trying to generalize everything in hyperoperational mathematics, I thought that I could generalize this to infinite divisions, basically. So we have infinite sets of numbers. I call them omegas, and we have omega 1, which contains integers, infinitely many integers, because there are infinitely many integers. A 2, which contains rational numbers, so all the numbers that can be created with division. 3, which contains all the roots that can be created with rational numbers, all the roots. Then basically we can calculate any omega. Normal numbers equals real. Well, normal numbers are the numbers that can. I think. Yeah, real. Yeah, right. Yes, right. Except normal numbers is what is called when a number is you cannot calculate the number. As I said, I literally said on this stream that I'm not good with explaining. I'm not good when it comes to explaining normal numbers. Basically, when it comes to normal numbers, you cannot write them down. It's not transcendental. That's the difference. For normal numbers, you don't even have a way to calculate them. One good example of that, well, the most common example, was a very boring normal number, is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Like, this number never repeats, and you cannot find an equation to calculate this number. It doesn't matter if it has, like, infinite multiplication or whatever. You cannot. And I'm pretty certain, might be missing something up, but that's the general idea of normal numbers, right? These are all there's all the numbers that, well, I would say, I'm not good at explaining them, just tell me you understand. Anyhow, that's good old working math. Now let's move on to math that isn't working, which is mine. What's really interesting is that these omegas contain every single number. Every single one. They just do. Because at some point you will have an omega that by the end, these omegas contain every single number. So what's really, because they all increase exponentially forever, so at some point there is omega n, which contains the number you are thinking of, no matter what that number is. Now, what that means is that there is omega n, which contains pi, e, or golden ratio. There is just omega that contains that. And over here, I create an equation for calculating basically a number inside a given omega based only on integers. So for example, for the first omega, that's just an integer. So yeah, an integer is an integer. For rational numbers, it's integer divided by an integer. For irrational numbers, that's an rational number. Well, not irrational numbers, only all the roots. That's a rational number rooted to the rational number. For the fourth, which is not even used in normal mathematics, it looks like this. And there is a way to calculate this for pi. That's an equation for pi. It would be unbelievably long. I at least assume. There is no way for me to know. I haven't actually. I just came out of that. But it will be unbelievably long, but it will be finite. Which is insane. Considering that all of the ways to calculate pi, how to compute pi. Fire hydrant, let's try it. I think it's pretty funny, the thing that I did here. I think it's funny. The only problem is that you will have to find the n and all of the x's, which is, well, as I said, marginally impossible. Maybe there is probably a way to do it. Maybe I could find one. But if there isn't, then, well, I mean, it is very much useless. I don't want to confuse anyone. This is useless. It is 100% useless so far. You cannot do anything with that. It's just fun. Like a decent thought experiment. Yeah, exactly. Yeah. That's exactly what it is. It is very much useless. You cannot calculate pi, but this is saying that you could. Which is funny, in my opinion. You can basically write a finitely long equation for calculating pi. By the way, I can also tell you why this doesn't work in normal mathematics. In normal mathematics, it doesn't work because we are not using hyperoperations. That's the kind of cheat code here. For example, because this one would be using hyperoperations of order n, which is, well, a lot. It's very much a lot. So, in reality, this is a very complex equation. It's not even long, it's very complex. And it doesn't have any complex numbers. That's very funny. Rather funny. Comical, if I do say so myself. I genuinely want to publish, publish this on my website, but in order to publish this on my website, I will have to add a huge disclaimer at the top, in red. This is not a scientific paper. Just so that no one would get any ideas. It's just a thought experiment. See what would happen if we used hyperoperations as a base for mathematics. There we go. Now it's safe. Maybe one day I will rewrite this as a scientific paper, but for now it's a mess. It's just a huge mess, so it's fun though. It's funny. Yeah, so there we go. There we go. This is, by the way, a heading 1. It's not a title. Should be very much a title. Now this looks like a forehead, but it's fine. NASA uses pi 50. Only 15. Oh, how cringe. My Ventum engine uses more. Let me see. Wait, how many Ventum engine uses? I want to see now. GitHub. How exact is my pi? Oh no, I think I only did E. I might have only done E. MKT multi-app. Let me see. It's inside source, if I'm not mistaken. Math. It's not inside start header. I'm pretty certain I defined E somewhere. Oh, maybe I didn't. Oh yeah, I didn't over here. Find it in 0 stars. How? Oh my goodness, I'm missing that fame. Yeah, but I defined it for myself because I for some reason I am not using almost any headers. Yeah, I thought I defined it in assembly. That's very upsetting. I genuinely thought I defined it assembly. I might have did it over here. No, this is me testing math. Didn't work out well. Just it did not. Okay, maybe I am not using any precision then. Absolutely horrible. Awful, awful. Anyway, that's one last thing I feel like I should just add this to my site. Just kind of, because I'm not gonna lie, I'm all out of ideas for this stream right now. We just proved that any number can be calculated, can be written down as a finite equation using only integers. And yeah, that's good enough for me. So let me just export that. File, download, and PDF, right? That seems... Let me just rename that to Hyper Operational Mathematics HOM 0. And throw it on my site. Unfortunately, I will not be able to show you the stream from that, for I am afraid that that I will show you something that I'm not supposed to. No idea what I could show you, honestly, but you know, better safe than sorry. There are actually many things that I could show that are pretty... well, yeah, most of this. I use denotation, but I don't think that Google actually uses LaTeX. I'm at least guessing. Okay, I just noticed that this file is quite literally called homo. That's... well, too late to change it now. Yeah, it's... I was using notation, but I think Google just formats notation to its own sort of thing. It's still rather funny. How heavy is that? Good question. My dear homo file. It's in kilobytes. That's decent. That's decent. Yeah, okay, I will not be able to right now. It requires me to set up a site for this. But so yeah, that was the thing, the stream, which I started by mentioning how dumb I am for the fact that I thought fixed points were real. I removed them, right? You packed your first domain. Oh, what is it? Sick. Oh yeah, that is actually smart. Makes sense. All right, understandable. I am going to my stream just in case once again. Let's say it. Sorry. That is actually, yeah, that is reasonable not to send on. Yep. I think I'll be ending this stream. I'm getting kind of hungry. Oh, tomorrow's day 69! How did I... Oh, I forgot completely. It's day 69! Fudge! Oh, how... I'm just so casually streaming day 68. Hi there. I'm just ending... You just... Hi there, friend. Kai. You, you really joined on the end of the stream. But still, glad you joined. There isn't much going on right now. I'm sorry. Right now, the tech and science part of the stream ended. It's just black screen with an ad on the bottom. All right, so as I said, I think it's time to go. It's been fun. It's been a fun hour. We did some writing. We did correct a mistake. Fixed points. I don't know. I thought fixed points were real. Something good. I'll have to think about that. Anyway, that will be it. Thank you everyone so much for watching, and have a great day. Bye.